The universe is so vast. There are countless planets out there. Alien life should be everywhere, right? But why haven't we seen a single trace of alien life? Scientists have discovered that our galaxy is actually located within a massive cosmic void, the KBC void, also known as the local void. This discovery might hold the key to unlocking the biggest mystery of the universe. There are at least 100 to 400 billion stars in the Milky Way. If each star has a planet, there could be as many as 400 billion planets in our galaxy alone. And across the entire universe, there are about 2 trillion stars. The number of stars is mind-blowing. There are even more than all the grains of sand on Earth's beaches. Naturally, the number of planets is also huge, but the reality is quite the opposite. With so many planets, we've yet to receive a single signal from alien life. There's no evidence suggesting that they're even trying to communicate with us. This is known as the Fermi paradox. When astronomers were studying the distribution of nearby galaxies, they discovered the KBC void. Using a technique called galaxy redshift surveys, they measured the shift in the light emitted by galaxies due to the expansion of the universe, and created a 3D map of galaxy distribution. What they found was shocking. A vast void with a diameter of 2 billion light-years, where galaxies were surprisingly sparse. This void is 7 times larger than typical cosmic voids. This discovery stunned scientists because it directly challenges 2 key principles in cosmology. The cosmological principle suggests that matter is evenly distributed throughout the universe, but the KBC void defies this idea, as it contains a stark lack of galaxies. Furthermore, according to the current lambda cold dark matter, lambda CDM, model, the Millennium simulation shows that gravity alone is insufficient to form a void of this size. However, with more and more observational data coming in, the existence of the KBC void is becoming undeniable. This massive void is no ordinary feature of the universe. It might even help resolve the Hubble tension, a problem that has puzzled scientists for over 60 years. The universe has been expanding since the Big Bang, and the rate of expansion is described by the Hubble constant. There are 2 ways to measure the expansion rate. The direct method involves observing nearby galaxies, calculating their distances using variable stars and supernovae, and then measuring their speed of recession to determine the Hubble constant. The indirect method observes the cosmic microwave background radiation and uses early universe models to estimate the Hubble constant. But here's the problem. The 2 methods give different values for the Hubble constant. The value calculated from nearby galaxies is about 73 km/s per megaparsec, while the value derived from the early universe is about 67 km/s per megaparsec. Don't underestimate this difference. It's significant. It leads to a 10% discrepancy in the estimated age of the universe. A higher Hubble constant gives us an age of about 13.8 billion years, while a lower value suggests an age of only 12.5 billion years. So, how does the KBC void explain this Hubble tension? It turns out that the KBC void has lower galaxy density, and when scientists analyze the material density in the void at a distance of 300 million parsecs, MPC, they found that, on larger scales, it's about 20% less dense than the average density of the universe. This lower density means that objects inside the void experience less gravitational pull, while denser regions around the void exert a stronger gravitational pull, creating an illusion that the universe is expanding faster than it really is. Previous studies have also found that the locally measured expansion rate is about 11% higher than the true rate. Thus, the low density of the KBC void provides a natural explanation for the Hubble tension. At the same time, the existence of the KBC void poses a challenge to the lambda cold dark matter model. This model is the currently accepted framework in cosmology, but it cannot explain the formation of such a vast void. When scientists adjust initial density fluctuations and increase the efficiency of structure formation in simulations, they can form voids like the KBC void. But at that point, the simulation no longer aligns with the lambda CDM model, and instead requires modifications based on the modified Newtonian dynamics (MOND) theory. There are 2 key differences between the MOND theory and the lambda CDM model. MOND modifies the way gravity works at low accelerations, substituting dark matter with a different gravitational behavior. MOND predicts that galaxies and galaxy clusters should grow faster than the lambda CDM model suggests. making it easier for cosmic voids to form. Currently, there is no consensus on which theory is correct, and different observations of the universe support both views. The true nature of the universe remains a mystery. Now, back to the Fermi paradox. The discovery of the KBC void provides a new perspective. First, there's the isolation factor. With so few stars in the KBC void, the chances of discovering intelligent civilizations are slim. If life is more common in denser regions, then being in the KBC void means we are far from other civilizations, which dramatically reduces the probability of contact or discovery. Next, there's the issue of distance and the scale of the universe. The galaxies in the void are so far apart that even if an advanced civilization's signal were sent in our direction, it would take an immense amount of time to reach us. In meaningful timeframes, it simply wouldn't arrive. So, direct interaction is almost impossible. Lastly, there's the avoidance factor. Perhaps advanced civilizations deliberately avoid less developed societies, or because we are located in a void, an area with a low population density, they might not even be aware of our existence. Intelligent life is more likely to evolve in regions that are rich in resources and have frequent interactions. Places like the KBC void are probably not even on their radar. In addition, the KBC void raises questions about the anthropic principle. The anthropic principle suggests that the universe is the way it is because we, as observers, exist. In other words, our existence in a low-density region like the KBC void may not be accidental. It could be a necessary condition for the development of life. If the universe were deadly everywhere, and there were no large voids, life might never have emerged. However, the scientific validity of the anthropic principle has always been debated. Some argue it is more of a philosophical argument than a scientific hypothesis. Regardless of how we view it, the discovery of the KBC void adds a new layer of mystery to our understanding of the universe.